Welcome to this tutorial on exact equation. In the previous tutorial we looked at equations reducible to separable form. I am Adetunbi Emmanuel Olukunle. So when do you say an ordinary differential equation of the first order is exact? Given the differential equation of the first order in the differential form, mxy dx plus nxy dy equals 0. This is said to be exact when you differentiate your hem with respect to y, let's call it my, and you differentiate your hen of xy with respect to x, let's call it nx partially, and your my equals nx. So a differential equation is said to be exact if the partial differential of m with respect to y is the same or gives the same value as the partial differential of your n with respect to x. So let's look at this example. Solve the differential equation 1 minus 2xy dx plus 4y cubed minus x squared dy equals 0. So what's our m? Our hem of xy for this question is 1 minus 2xy, and our n of xy is 4y cubed minus x squared. So when you differentiate m with respect to y, what do you have? This is 0 minus 2x, which is minus 2x. If you differentiate n partial respect to x, when you differentiate 4y cubed with respect to x, that is 0. When you differentiate x squared, you get 2x. So that is minus 2x. So we can see clearly here that our my equals nx. So we say that the given first order ODE is exact. So when it is exact, how do you solve it? Please, I'd like you to listen very carefully. I want to give a very simple approach to solving this. If you pick the first function as the pivot function, you integrate everything. That is integral 1 minus 2x y dx plus. You now look for the term in the other function that does not contain x. Since this is dx, look for the term in the other function that does not contain x. So the other function is that is n, that is 4y cubed minus x squared. So 4y cubed does not contain x. So we integrate 4y cubed with respect to y. Then you equate your value to c, the constant of integration. So let's integrate this. 1 with respect to x, that is x minus 2x squared on 2y plus 4y 4 on 4 equals c. This gives us x minus x squared y plus y to the power 4 equals c. Then we are true. Alternatively, we can decide to pick the second function as a pivot function. That is integral 4y cubed minus x squared. We integrate everything. So since this is the y, we look for the term in the other function that does not contain y. The other function is 1 minus 2xy. So 2xy contains y, so we won't touch that. We only have 1, so we integrate 1 with respect to x. Since the first one, which is the pivot function, is with respect to y, we're integrating with respect to y. The second one, the subordinate, will be integrated with respect to x. You equate the value to c. So when you integrate 4y cubed with respect to y, you have 4y 4 on 4 minus x squared y plus, when you integrate 1 with respect to x, you get x equals c. So you have y to the power 4 minus x squared y plus x equals c, which is the same thing as what we obtained when we picked the first function as a pivot function. This is why it is called exact. So whether you pick the first function as the pivot or the second as the pivot, just look at the rule very well. Once you don't break the rule, you're going to have the same value. Hope this is sticking. Let's look at another example. Solve the differential equation y cos x plus 2x exponential y plus sin x plus x squared exponential y plus 2 the y dx equals 0. This question we have. So let's multiply through by dx so that it can take the differential form. Sin x plus x squared exponential y plus 2 the y equals 0. So here our m of xy equals y cos x plus 2x exponential y, and our n of xy is sin x plus x squared exponential y plus 2. So we check for exactness. That's the first thing we do. Let's differentiate m with respect to y. That's the rule always. If you differentiate y cos x with respect to y, you get cos x. If you differentiate 2x exponential y with respect to y, you get 2x exponential y. Okay. Now let's differentiate n partial with respect to x. If you differentiate sin x with respect to x, you get cos x. If you differentiate x squared exponential y with respect to x, you get 2x exponential y. If you differentiate 2 with respect to x, you get 0. So clearly, our my equals nx. So the given first order ordinary differential equation is exact. So how do we solve it? I love picking the first function because it is the closest as a pivot function. So I will integrate everything. Y cos x plus 2x exponential y dx plus, I'll look for the term in the other function that does not contain x. Sin x contains x, x squared exponential y contains x, so 2 does not contain, so I integrate 2 the y, equates the value to c. Okay, integrating y cos x, I have y sin x, okay, plus this is 2x squared on 2 exponential y plus 2y equals c. So I have y sin x plus x squared exponential y plus 2y equals c as the solution to the given first order ordinary differential equation that we found out to be exact. Now let's look at the third question. Solve the differential equation 3x squared plus 2xy plus x plus y squared the y dx equals 0. To assume the differential form, multiply through by dx. So we have 3x squared plus 2xy dx plus x plus y squared the y equals 0. So here our hem, the hem of xy is 3x squared plus 2xy, and our n of xy is x plus y squared. Okay, we have to check for exactness. So my, differentiating m with respect to y gives us 2x. Differentiating n with respect to x gives us 1. So my is not equal to nx, so the equation is not exact. So how do we solve this? The only way we can solve this is if we have what we call the integrating factor. We'll look at that in the next tutorial. Please let me leave you with some questions for you to attempt. So solve the following differential equations. X plus sin y plus x cos y minus 2y y prime equals 0. Number 2, y plus xy prime equals 0. Number 3, 3x squared y squared plus 2x cubed y plus 4y cubed y prime equals 0. Number 4, y dx plus 1 minus x the y equals 0. With the aid of the example we've treated, it should be very easy for you solving these questions. If you find out that you need the integrating factor, you just stop. Maybe by the time we look at the next tutorial, you'll be able to solve the equations. That has brought us to the end of another tutorial. In the next tutorial, we'll be looking at the linear ordinary differential equation of the first order. Please do join me then. I remain Adetunbi Emmanuel Olukunle. Thank you.